Hi everyone. In this video, we will be talking about what are finite automatas, and I will be giving you a brief introduction on what a finite automata looks like. So let's get started. Firstly, when a machine works, we can always represent it in the form of states. And finite automata is one kind of a machine which has finite number of states. Finite means countable. So in this case, finite will mean that countable number of input letters or input symbols in an alphabet. So this sigma, the set of input symbols, will be finite. Then your transitions, that is moving from one state to another, those set of transitions will also be finite, plus the machine that is represented in a state is also finite. So the number of states, the set of states, is also finite. So a finite automata means that it works on countable set of three things: your input alphabet, the set of transitions, as well as the set of states. And automata means that it works on its own given some input. So there are certain rules that will define each automata, and given the an input, it will keep jumping from one state to another automatically. That's why it's known as a finite automata. Now, if you look around, there are a lot of automatic machines that you might have seen. For example, a fan. For example, your washing machine, refrigerator, microwave oven, all these things are finite, are some kind of automata and can be represented in the form of states. Some automata may be finite, some may not be finite, but let's keep our focus to finite automata for this lecture. Now I will be moving to an example of a vending machine that dispenses your favorite snack, and I will tell you how to represent that vending machine as a state. Consider this vending machine. So for simplicity's sake, I have numbered all the states in the machine. So let's assume that minus is my start state, the state 1, followed by second state, third state and fourth state being final. It is taking some inputs, and on those inputs it is moving from one state to another. And these edges between the states are directed edges. Now, if I tell you how a vending machine works, suppose you go to a metro station or probably your favorite shop and there is a vending machine. What do you typically do? That kiosk is generally asking you to input what you want to have, and you input your choice, and then it asks you, do you want something else? So if you want something else, you just simply press a no, or sorry, a yes, and then you keep on ordering till you are done with your order, and then you say that I'm done, and you press a no, you make the payment, and then you quit. So I am representing this scenario in a state machine, in a state diagram. So if I go on to explain this diagram, you see that on an initial state, the start state, the kiosk was simply there. You went to the kiosk, you entered that you wanted an ice cream cone. So you ordered for an ice cream cone. In state 2, the machine asked you whether you want something else. If you entered a yes, you would again go back to the main menu. You could select your choice, and you will keep on doing this till you are done with your order. If you said that you are done and you said no, you could move to state 3. And moving to state 3, some computation was done inside to calculate your final bill. Now, in a state diagram, in an automata diagram, we are only going to talk about these states, these transitions on the input symbols. What is happening inside the state, we will not be talking about. So let's assume some way or the other, this particular state has computed your final bill. You inputted your final payment, let it be a token or a credit card or a payment card, and then you quit. So you reach the final state or the halt state. So I have represented a complex vending machine in a very simple way. Of course, there are a lot of cases that I have not covered over here, but this is a very simplistic representation. And now I told you how, based on your inputs, a machine moves from one state to another. Let me give you another example of a fan. So, if I give you an example of a fan, so an electric fan, how does it work? Initially, it is an off state. Okay. So let me represent that initial state, that is an off state. Let me call this as state 1. You could call it anything x1, x2, x3, a, b, c, d. We try not to number these states same as the input symbols to avoid confusion. Now, on an input of on, so you switched on the button. On an input of on, you move to state 2, and you on moving to state 2, the fan started rotating, and let's suppose you wanted to increase the speed, so you move to state 3. Here you move to state 3. Now in state 3 you realize, okay, the speed is too high, let me decrease the decrease the speed. So see, again, this is very simplistic representation. There are many possible speeds in an average fan, but I am taking just increased and decreased speed option. So on increasing speed input, you move to state 3, and on decreasing speed input, I move back to state 2. Now, suppose at any given point of time you wanted to switch off the fan. So, you can go back to this initial position when the fan was off, and which was your state 1. So, this is your state 1. And this could be done from state 3 also. On off, you can always say, okay, I want to switch off my fan from here. So, you have done this. So I have switched off the fan and moved back to the state 3. So now nothing is happening after switching off the fan. Let me call this as my halt state. So an initial state is also becoming a final state in this case. So if you see the functioning of a fan, when you switch it on, you move to another state. You increase the speed, you move to another state. You decrease the speed, you transition to another state. On switching off the fan, you move back to the initial state, which also happened to be a final state. So here what we are doing, we are just representing the functioning of a fan using a state diagram. And if I want to say, okay, so what are my input symbols for a fan? So your input symbols are what? Firstly, you can say that, okay, I want to switch it on. Yeah, I want to switch it off, and I want to increase speed, or I want to decrease speed. So these are my input symbols, possible input symbols. So I have found my alphabet here. Also, if you are in a state of off, so on no input or on an off input, you will remain in this state. Okay, so this is also a possibility. I stay in this state itself. So on off, that is, I am not pressing any on button. So I am sitting in the state of itself. So these are my input symbols. And what are my states? The state set could look like S is equal to 1, 2 and 3. So this is the set S of states. So this is the set S of states. And the transitions could be transition 1, transition 2, transition 3, 4, 5, 6. There are 6 transitions. These are also countable. So you could represent these transitions in a set called delta, and you could simply say 1 to 2, 2 to 3, 2 to 1, 3 to 2, 3 to 1, and 1 to 1, so on and so forth. So all these transitions could have been represented in this. So all the finite automata are typically constructed with a finite alphabet sigma, finite set of states, and finite set of transitions. And of course, if I look clearly, there is generally one initial state and zero or more final states and some intermediate states in between. In case of a vending machine, you have one initial state, one final state, and two intermediate states. So we represent minus sign to represent the initials or a start state, and we use the plus sign to represent the halt state or the final state. Now, what is happening over here? If I talk about my vending machine, let's say my vending machine offers this ice cream cone. Let me call it icy, and let me call, say we are representing a veggie sandwich, or let me just erase this slide, and let me say that, okay, C represents the ice cream cone and B represents the veggie sandwich, and let it offer me a soft drink. So these are the three possible things that this vending machine dispenses. Apart from this, it also takes input, what, yes or no, for the user's choice. And apart from this, it also accepts payment, over here. So I can say my payment could be a token like this, that is shown over here. So this is a token, or probably you can say a card. Okay, so you are this machine is accepting a card also. So CA. So my input set of symbols is this, in this case sigma equals to this. So cone, veggie sandwich, soft drink, yes or no choices, token, and card. So and my set of states is 1, 2, 3, 4 finite. Now let me say that there is a string that comes like this. Let's say a string where I enter the choice of cone, and then I say yes, I want something more. Then I say okay, I want a veggie sandwich also, and then I say no, I don't want anything else, and then I say token. Let's say there is this input string. Okay, so input string means this input string is being given to this particular machine, and let's see how this machine processes this string. So it is going to process the entire string. See, this string will be of some finite length. This length could be anything, but this string will be of any finite length, and all the symbols will have to belong to this, nothing else. So this input string will be processed one by one. Let's say in the state 1, the machine sees a cone. Okay, I can accept a cone. Then the machine moves to state 2. Now on moving to state 2, we say okay, we are over y. In state 2, if there is a y, you go back to state 1. Okay, move to state 1. Then this y was also processed. Then we move to state 1 and we read a v, which is your veggie sandwich. Okay, on reading a veggie sandwich, we move back to state 2. Okay, now I am in state 2 and I get to see a no. Got a no. Okay, fine. So no is processed, that means we can move to state 3. Now moving to state 3, we read a token. So let's assume that this token was a payment. So on reading the token, we move to state 4. The entire string was accepted and you got a blank thing. So that my string is over and I landed up in the final state. So for a finite automata given a string, if on completion of the string you land up in your final or halt state, you say that this string is accepted by the finite automata, and this string becomes a word in the language accepted by the finite automata. Let me take another example. Let me say, okay, my input is a veggie sandwich. Then I say a yes, and then I say a soft drink. Okay, so what happens? I am in state 1. I get to read a V. Okay, move to state 2. I get to read a yes. Move back to state 1. I get to read a soft drink. Okay. Now I move back, I read a soft string, I move to state 2. In state 2 there is this blank symbol. My string has finished, but am I in the final state? No, I am not in the final state. So this string is not accepted by the finite automata above. And because this string is not accepted by the finite automata above, this string is not a part of the language accepted by the finite automata, or this string is rejected by this finite automata. So I hope we are clear about this. Any string in a finite automata, when the string is finished and you land up in your final state, we say that the string is accepted by the finite automata and is a word in the language accepted by the finite automata. So this is what we have explained so far. Minus is your initial states, there are some intermediary states, and plus is your final or halt state. So if I talk about finite automata more formally, it's a state diagram. It captures all possible states and transitions to other states on all possible inputs of alphabet. So in this case of the vending machine, I have captured all possible states, but I have not yet captured all transitions and all possible inputs. For example, in this case, I have not said that what happens we get a veggie sandwich or a soft drink, and what happens here if we get a veggie sandwich over here or soft drink over here. So what happens if in state 3 we get veggie sandwich or soft drink as an input. So I have not talked about that transition, but I will be covering it in the next lecture on how to tell all the cover all the possible transitions on all possible inputs in the state. Okay, so a stream of inputs or a string, the finite automata will respond to on the input symbols, and it will be read, the stream of inputs will be read one by one and help you transition automatically from one state to another. And if after the end of the input string the machine is in final state, we say that FA accepts that string. FAs recognize regular languages. This is important to note that FAs recognize regular languages. So, for every regular language, you can build up a finite automata. It is finite because your states are finite. Remember, regular expression is a finite representation. The number of symbols are also finite. So is the case in regular expression. And automata will help you state changes based on inputs. So how to build a finite automata from regular expressions, that we will talk about in my upcoming videos. Till then, I hope you are clear with what basically is a state representation of a machine and how to build an automata. We will be covering more of the finite automata in my next lecture. And if you have any questions, please write to me in comments. You can like this channel, you can share it with your friends, and subscribe to this channel to keep learning. Thank you.